Hey chemistry students, Mr. Ferguson here, and we're about to start lesson 10.3 where we look at Boyle's law and Charles' law. We want you to be able to state both Boyle's law and Charles' law, and we want you to solve problems using these laws. And lastly, we want you to recognize directly proportional relationships between variables and inversely proportional relationships between variables. And hopefully you'll be able to recognize them from looking at an equation or a graph or a data set and kind of pick out which one of those relationships is going on. So let's get started. So we have various properties that we can measure for gases, and we've talked about those already. Pressure, how hard it pushes against its container or
volume,
surfaces.
the amount of space that it can take up,
The temperature that the gas is at,
which is also the average kinetic energy,
and then the number of particles, which would be a measure of the amount of gas that you have.
and we can solve that from stoichiometry if we wanted to. If we have so many moles, we know how many particles we have, or how many grams, liters, etc. You can solve for number of particles.
So, and these things are all interrelated. For example, if we have a balloon, it has a certain volume. Well, if we take a deep breath and blow some more air into it, so we increase the number of gas particles, what's going to happen to its volume?
Well, assuming it's not a super rigid balloon, it will increase in volume, of course.
So there's a relationship there.
If we take that same balloon and leave it outside over a nice cold night, the balloon would, of course, then
Get smaller.
deflate.
So we didn't let any particles out, but there's a connection between temperature and volume. And then, of course, there's a connection between number of particles and pressure. If we have, say, a rigid container like you talked about, like a tire, a car tire, you force more air particles into it, you're not going to see the tire swell and expand. It gets so big, and
at
then
a certain
the pressure
point, yeah,
starts to go up, so there's a
increase.
connection there. And of course, there's a connection between the pressure of a gaseous system and its volume.
And pressure and temperature,
And
they're all
interconnected. So the main point is that when we talk about gas laws, they are mathematical relationships that connect one of these properties to another. And so by the end of this unit, we're going to look at a number of different gas laws that look at first two of the variables, and then we'll add in maybe a third one when we do our combined gas law, and then we'll put it all together and put them all together in the ideal gas law at the end of the unit.
All right, let's take a look at the first gas law then.
So we're going to attempt to derive Boyle's law, and the apparatus that we have set up is shown in the screen at the right. This is a syringe, and we've got a small amount of gas captured there. And this is an absolute pressure sensor. It's hooked up here, and then the circuitry connects in. We get a reading in kilopascals. So you can see the initial syringe reading is saying 10, but we also have that little bit of space here in the tube that connects to the sensor. We've estimated that to be about 1 milliliter. So for our initial volume, we're going to record that as 11.0 milliliters. And our initial pressure is 99 kilopascals. So let's play the video back and see what happens when we change things.
So at 6, even though it says 5, remember to add the 1, it's 183. And then we take it out to 15, which would be 16 because they add the extra 1. And that would be 68.
So looking at the data, we can see that when we had the smallest pressure, which was in the last instance, we had the largest volume. And when we had the largest pressure, which was in the second instance, we had the smallest volume. So they when one goes up, the other one goes down.
So then to actually derive Boyle's law, we multiply these two together, each pressure to volume, and we found that with proper sig figs, they all go to 1100 as a value.
So you have to round them up, but if we go with the two significant figures, which is the smallest number in each set of two we're multiplying, the product of pressure and volume is the same, or in scientific terms we would say when it's the same, it is a
constant.
It's a constant value, and that's basically Boyle's law.
All right, so Boyle's law states for a given quantity of gas at a given temperature, pressure, and volume are inversely proportional.
And you should write that down.
Yes, and the equation comes in two forms. We have Boyle's law as P times V equals K1. That's just what we proved in the last slide. If you multiply the P, pressure, and the volume of any given system, it's always going to equal the same value, K.
So that K is just like a generic constant.
Yeah, it can equal any number. Or, it's knowing this, that we know the system is, on the same system is equal to K1. If we have two separate sets of conditions, like P1 and V1, so that's pressure 1 and volume 1, and then we change, let's say, the pressure on it, that'd be P2, we can use this to calculate what the new volume can be. So this is a very powerful tool in predicting what should happen to a given system. And of course, Boyle's law in a graph, we show that as volume increases, pressure decreases. So what type of relationship would this be known as?
This is an inverse proportional, or inverse proportion. So just what Mr. Hunter said, when the pressure gets larger, the volume gets smaller by the same factor.
Yep.
If we double the pressure, you would half the volume.
Yep.
That's the idea of an inverse proportion. One gets bigger, the other gets smaller by the same factor.
All right, let's look at the next law.
So we're going to derive Charles' law now, and this is a little more problematic because we need to compare volume and temperature at a fixed pressure for a fixed sample of gas, and it's a little harder to get something that can change its volume. We could use a syringe, but they don't tend to move very freely. So anyway, we found a graphic. It's not quite as good as doing it for real. So the graphic shows at minus 10 Celsius, there's the volume of the balloon.
Mm-hmm.
And then at 0 Celsius, 10 degrees warmer, there's the volume. And at 10 degrees Celsius, there's the volume. Now, of course, we needed to convert those temperatures to
Kelvin.
So that's what we've done here by adding 273 to each temperature. And then we wrote the temperatures down here next to their volumes.
And took the volume divided by the temperature. And in each instance, we got the same answer of 0.00366, which tells us once again that this derives out to be another constant.
So the ratio of volume to temperature is a constant value for any given sample of gas at any given pressure.
Okay, and now we're going to go on to a practice problem. So Charles's law says for a given amount of gas at a constant pressure, the temperature and volume are directly proportional. Directly now, not indirectly like last time. So Charles's law in an equation, of course, is volume divided by temperature, again, equals some constant.
And that constant's value is going to be determined by the amount of gas and the pressure you're at this particular system.
And these are always dealing with the same system. So it would be the same balloon or the same container. You can't go from one balloon to another balloon and expect to get the same K value. So if we then take this, we can now put them equal to each other, two different systems or two different conditions of the same system, and that way you can take V1 divided by T1 equals V2 divided by T2. Of course, you know the initial volume and temperature of a system. If you change the temperature, you can then predict what should happen to the volume, or if you change the volume, you should be able to predict what happens to the temperature. Again, it's a useful tool. So if we look at the graph for this, you'll notice as temperature goes up, volume goes up, and as temperature goes down, volume goes down. So again, this is a directly proportional relationship, which means as one increases, so does the other.
By the same factor.
Yeah.
Okay, so this is a very different shape graph than our inverse proportion. All right, let's get to some practice problems where we can apply these two laws.
So before we start, we have to rewrite these laws. Boyle's law is V1 times P1. All right, reverse it for me, why not? To P2, V2, and then V1, T1 equals V2, T2. So those are our two laws in question. So our first problem is if we have a balloon and it has a volume of 2.5 liters at 1 atmospheres, what will be the balloon's volume at 3 atmospheres? So we have two different sets. We have our initial conditions, V1 and T1, or V1 and P1 right here, and then we have our second set, which would be P2.
So the first thing, I guess, we have to decide which one of those relationships do we want to use here.
We need volume and pressure, so that leaves us
All right.
that one. So let's set it up. So it's going to be 2.5 liters.
How about I put it on pen?
Yeah, you could.
2.5 liters multiplied by 1.0 ATM
Equals X divided
X
by
times
3.0
atmospheres.
So this is going to be 2.5 times 1 divided by 3 to give us a new volume of, give us a new volume of 0.83 liters.
0.83 liters, and of course the units do work out because we end up with atmospheres over atmospheres, so they cancel one another
Leaving
out.
us with liters at the top.
So that's just, that's how they go. You get 3 of the 4 things. You find the 4th one using a little basic algebra.
The next one we have at 25 degrees Celsius, a sample of gas in a movable piston has a volume of 75 milliliters. What is the volume of gas when its temperature is raised to 89 degrees Celsius? Well, the first issue is we are in degrees Celsius. We can't deal with degrees Celsius when we are doing gas laws, so we have to convert them to Kelvin. So it's going to be 25 plus 273. Wow, I'm on calculator. Equals 298. And then 89 plus 273 equals 362 Kelvin.
We have to use Kelvin or you're not going to get
the right
correct
answer.
because we need a scale that starts at 0 when there is 0 particle motion.
So now we have to decide which equation we want. We have a volume and a temperature. So I would go with Charles's law, V1 divided by T1 equals V2 divided by T2. You would set them up. So V1 is 75 milliliters divided by
298 Kelvin.
298. And then we have to multiply both sides by 362. Because this is how math works. Simple algebra here.
So this
side
entire
cancels.
thing cancels itself out, unit and number.
And on that side, our kelvins cancel out, leaving us with milliliters. So we're gonna.
You don't have to change the, as long as you want your answer in milliliters.
As your volume's the same. Yep.
You're okay.
So we're gonna end in 91.1.
0.1. So with sig figs, we'll
91,
go 91.
I guess.
91 milliliters is the volume in the second condition.
You can see how easy these are. We'll be doing some practice, of course, in class. But in the meantime, have a good night, and we'll see you tomorrow.
See ya. Alright, so to wrap up this lesson, here's 2 post-video questions. One uses Boyles and one uses Charles' law. So in the first one, you know the volume and temperature that a gas is at, and we've changed the temperature by 100 degrees Kelvin, or 100 kelvins. You are supposed to predict the new volume. So that sounds like a Charles' law problem to me. So see what you can do with that one. In the second one, we're told the pressure and the volume of gas in a balloon, and the air pressure changes, and you are to predict the new volume. So this one would obviously be a Boyle's law. We have one little additional wrinkle we've thrown in. You might have picked this up already. The first pressure is atmospheres. The second one is in kilopascals. So you're going to have to do a little bit of a conversion one way or another in order to get both those pressures to the same unit. So give those a try, and we'll talk about them next time in class.